So today we'll be talking about solving recurrences. What are recurrences? Recurrences are equations that represent the running times of divide and conquer algorithms. So a recurrence is an equation. We will first write this equation for merge sort, and we will solve it for merge sort. Then we will study general techniques for solving these recurrences, for solving these equations. So first of all, before we start talking about the analysis, let's revisit the code for merge sort. So this is the code that we wrote last time. This is the base case. This is dividing the array in half. Then we call merge sort on the left hand side. Then we call it on the right hand side. Then we merge the two sides. Okay. By the way, there will be a programming assignment in which you will implement this so that you can understand it very well. Now in the code that we wrote last time for the merge, there was something missing. When I looked at the lecture, I noticed that we forgot something. This was implied, but we should write it explicitly. So when we created two temporary arrays, L and R, we did not actually copy, even though that was clear, from the that was very clear from the description of what L and R are. But we need to copy A from P to Q into L and A from Q plus 1 to R into R. So this is A, this is A, this is P, this is Q, Q plus 1, and this is R, and this is L, and this is R. Or let's do L and R. So basically last time, the pseudocode that we wrote last time, it was missing these two lines, that we have to actually do this copying. Okay. Okay. So now today's lecture is going to be about the analysis of the algorithm. Our first example on divide and conquer. We will see that merge sort is a relatively easy algorithm to analyze. Then we will generalize this and learn how to write an equation that represents the running time of a divide and conquer algorithm, and we will learn general techniques for solving these equations. So if we think about the running time of merge sort, so who can give me an analysis of who can analyze the running time of merge sort? So in a previous lecture, it looks like people knew what the running time of merge sort is, but where did that runtime come from? How do we analyze it? Yes?
Merge will take O of n.
Okay, so this is a good step. This is a good first step. So this by itself, this is theta of n. Because this is linear time. This merge is going to be, it's a loop. Basically, it's a loop. And it does one comparison. Or if you look at the loop, k equals p to r, what's inside the loop is a constant. So it's a loop that goes from p to r, and what's inside the loop is a constant. So in fact, for any subarray that goes from p to r, the number of steps is going to be the difference between r and p. So it's r minus p plus 1. Well, it's theta of n for every n, for every level n, or for every pair of values p and r. But if you if you draw, so let's draw size 4. So this is size 4, then size 4 is divided into 2 and 2, then 1. Okay, so at this level, this is P and this is R. At this level, there are two. This is a P and this is an R. But then at a later point in the algorithm, this will be a P and this will be an R when we are merging this. Then, so what did I do? So this is divided into two, sorry. Then at a later point, this will be P and R, then this will be P and R, PR, PR. Of course, in which order? So which two arrays will get merged first? Yeah. So the first merge is going to be this and this. So will be this and this will get merged into this. Then this and this will get merged into this. Then these two will get merged into this. But this is theta of n, which means that the difference between P and R here is going to be n. But at this level, this is n over 2 and n over 2, roughly. So this is half n, this is half n, but the total is going to be n. And here, each one of them is going to be n over 4, n over 4, n over 4, n over 4, and the total is going to be n. So what it means is that at each level, in fact, in this case, we only have two levels of merging. So we only merge these into this, and then we'll merge these into this. So in fact, at the base level, there is no merging. But if we have, if we add another level, like this is a 4, and then we have level 8 with size 8, okay, then again, it's going to be n all the way. So this is n over 2, n over 2, and this is with the new n, this is n over 4, n over 4, and there will be 4 of them, 4n over 4. So this is going to be n. So the idea is that at each level, the work that we will be doing will be theta of n, because the actual work at each level is done in the merge routine. This is constant. This is constant. And how about these? So how do we count these? How do we count the recursive calls? So the recursive calls belong to the next level. So we are trying to count the number of levels and the number of operations at each level. So when we are counting the number of operations at this level, okay, we count this, but we do not count these. These will be counted in the next level. Next. These belong to the next level. The recursion is just like you are making a new call, and then it's in the next level, and you will be doing the same counting within the next level. So at each level, the actual operations are constant, constant, and theta n. Now the question is, what's the number of levels? What's number of levels for merge sort?
Log n.
Yeah, log n, because we go 8, 4, 2, 1, or 16, 8, 4, 2, 1. So the number of levels equals theta of log n. In fact, it's log n plus 1, but we don't care about plus 1. So it's theta of log n. So the running time of merge sort, to analyze merge sort, we just say that there are theta of log n levels, and the work at each level, or the number of operations is more precise, the number of operations at each level is theta of n. Therefore, the total running time T of n equals theta of n log n. Okay, So in fact, this is what we will be doing in analyzing all divide and conquer algorithms. So we will be trying to count the number of levels and count the number of operations at each level. But some of the algorithms are going to be harder than this because the number of operations at each level is not going to be the same. So each level is going to have a different number of operations. The number of operations at a certain level will be different from the number of operations at the next level, and so on. What makes merge sort easy to analyze is that the number of operations is the same at all levels. So because you divide it into two subarrays, and the array gets smaller by a factor of 2, but there are 2 of them. So this is half the work, half plus half is going to be n. And at the next level, the size of each array is 1/4 of the original size, but there are 4 of them. So this will give you n again. Okay, that makes it easy to analyze. But now, how do you think we will be analyzing an algorithm when the number of operations at each level is different? So it's not the same number of operations at each level. Each level is different. How do you think we will be doing this? In fact, there is only one way of doing it. We have to do a summation, right? Right. So when, like we said before, when there are 10 people and each person has the same amount of money, we just multiply. 10 people, $10, 10 by 10, that's 100. But when there are 10 people and each person has a different amount of money, we'll have to do a summation. And as we will see, there will be a summation when the number of operations at the different levels is different. Okay. Now, let's learn how to write an equation, a mathematical formula that represents the running time of a divide and conquer algorithm. So we will use merge sort as an example. Okay. So this is how we write an equation that represents the running time of a divide and conquer algorithm. We will say, okay, let T of n be the running time of the algorithm. So we just call it T of n. That's the running time of the algorithm, which is the total number of operations that will be executed when the input size is n. Now, the running time for this is equal to, well, this is a special case. Now, this is the base case. Base has a different treatment. We'll see how we treat the base. In fact, we will just say T of n, or let's write it in black. T of n equals a certain constant c when n equals 1. Now for n greater than 1, so the base case is executed when n equals 1. When n equals 1, the running time is just a constant. Now when n is greater than 1, we will execute all of these. So we will do this. Now what does this step do in merge sort? Yeah, it divides the array into 2 subarrays. So this is the divide step. Divide. This is the divide time. And in fact, the merge is the combine time. Is the combined time. And these, now how do we treat these? how do we handle merge sort these recursive calls? So this is the time for, if T of n is the time for sorting an array of size n, what will this be? Yeah, so this will be the time for sorting an array of size n over 2. So this is T of n over 2. And this is another T of n over 2. So now the formula is, if n equals 1, we have a constant. If n is greater than 1, we have the divide time, which is a constant. So we'll call it C2. Let's call it D. The divide time, let's call it D. D plus the combined time. What's the combined time? The combined time is theta of n. So it's D plus theta of n plus T of n over 2 plus T of n over 2. This is if n is greater than 1. Let's make sure that we understand this. So we're saying that the number of operations needed to sort an array of size n is equal to a constant for dividing it in half plus theta of n to combine plus the time for sorting half of it plus the time for sorting half of it. So this is sorting half, combining, and this is the combine. So this is the divide. This is the combine. And these are the recursive, these are the times needed to solve the smaller problems. Okay, so now, because this is constant and this is theta of n, what's theta of n plus constant? Theta of n. So this is a lower order term, so it will get neglected relative to theta of n. So this means that the formula is T of n equals C if n equals 1, and it's 2T of n over 2 plus theta of n if n is greater than 1. So this is what we call a recurrence or recurrence equation. Recurrence or recurrence equation. It's an equation that represents the running time of a recursive algorithm. So a constant for the base case, and for the non-base cases, this is 2 times the running time for each half plus the linear running time for merging the two. Okay? And in fact, sometimes it will be easier to write this as this is the theta of n. We write it as Cn. Oh, well, I can't use that, so I should use something else. So I use D here. Okay, so this is D and this is C, or whatever. You can use, just use different constants. Okay, now how to solve this? Well, we will study 2 methods. The recursion tree method and the master theorem method for solving these recurrences. Okay, so now okay, so again, this is the recurrence that we are trying to solve. D if n equals 1, 2t of n over 2 plus Cn if n is greater than 1. So now we are writing this base case explicitly, but later on we'll start dropping the base case, because in almost all the examples that we will be going through, the base case will have a constant running time for the base case, and the value for the size of the base case will be will not necessarily be 1. It could be 1 or 0 sometimes, but no matter what, it will be a constant for n less than or equal to a certain value. So generally speaking, it's going to be t of n equals some d for n less than or equal to some n0, and it will be something else, some other function for n greater than n0. So later on we'll start dropping this, because it will always be the same. There is always a constant running time for the base case, basically, and we will not be writing this explicitly. We will be assuming that it's known that the constant running time, the running time for the base case is constant. Okay, now the recursion tree method will solve this as follows. So it will say, okay, this is t of n, but t of n, I'm going to do some substitution. So t of n is going to consist of 2t of n over 2 plus cn. So t of n, I can expand it as cn plus t of n over 2 t of n over 2. So I have expanded t of n into cn, this cn, plus t of n over 2 plus another t of n over 2. So I did one expansion, but I can keep expanding. So I can expand it further and say, okay, now this is going to be cn, and now I'm going to substitute for t of n over 2. Now what's t of n over 2? T of n over 2 equals, so this tells you that t of x equals t of x over 2, 2t x over 2 plus cx. So substitute n over 2 for x. Let x be n over 2. Then this will be what? 2t n over 4 plus, what's x? X is n over 2. So it's going to be cn over 2. T of x equals 2t of x over 2 plus cx. So just substitute n over 2 for x. And this will give you t of n over 2 is t of n over 4 plus cn over 2. So now I substitute for t of n over 2, cn over 2 plus t of n over 4 and another t of n over 4. And I will do a similar substitution for the other t of n over 2. So that's going to be c n over 2 t n over 4 plus t n over 4. Now I have made two steps or two levels of substitution. I started with t of n, then I substituted for t of n, then I did the substitution for t of n over 2, and I can keep going, right? I can keep going, and I can substitute for t of n over 4. T of n over 4, I will substitute something. It will give t of n over 8, right? And then t n over 8, it will give t n over 16, and so forth. So I can keep substituting. So normally we only do a couple of substitutions to understand what's going on. Then we realize that this will give us a tree that will end at the base case. So we draw the tree like this. It's going to give us cn, then cn over 2 Cn over 2, then Cn over 4, Cn over 4, Cn over 4, Cn over 4, and we will keep going until we eventually reach a size of 1. And at the base case, so this is our base, at the base, we will hit the base case, so we'll have this D, D, D. Now, how many D's in this case? How many D's? Yeah, there will be n D's. Okay, so now how do we analyze this? In order to analyze this, basically we just count the number of operations at the internal nodes and count the number of operations at the base level. Now, in order to count this, let's review the mathematical relations between the height of the tree and the number of leaves and the number of nodes. So let's put this on hold for a minute and review the mathematical relations for a binary tree. For a complete binary tree, will look like this. This is a complete binary tree of height. So this is level 0, level 1, level 2, level 3. So this is a complete binary tree of height 3. Of height 3. Now, the number of nodes at level I equals what? Yeah, 2 power I. Exactly. Now, number of leaves L equals number of nodes at level H, and that's 2 power H. It's 2 power H, which is the number of leaves, the number of nodes at level H. In this case, H equals 3. In this example, H equals 3. Number of leaves at level number of leaves L is equal to the number of nodes at level H. So now if this is the number of leaves, so the number of leaves is an exponential function of the height, and of course the inverse function, the height is a logarithmic function of the number of leaves. So H equals log L base 2. Now total number of nodes, how do we calculate the total number of nodes? N. So if we know the number of nodes at level I, we can do a summation to calculate the total number of nodes. So that's going to be summation of I equals 0 to H of 2 power I. So total number of nodes, we just sum the nodes at each level. The nodes at level I is 2 power I. So we sum them from 0 to H. Now what kind of series is this? This is a geometric series. Yeah. This is a geometric series. So just to remind you of the formula for the geometric series, think we don't need this. So geometric series. So it's sigma x power I as I goes from 0 to m. What's the summation? So again, if you forget this, just like the arithmetic series, the other time we showed how we can derive the formula for the arithmetic series. Again, the formula for the geometric series, you can derive it like this. Summation equals x power 0 plus x power 1 plus x power m. You multiply this by m. If you multiply this by x, sorry, x times summation equals x power 1 plus x power 2 plus x power m plus 1. Right? So this is the summation. This is the summation multiplied by x. So this gives you, this is equation 1, this is equation 2. So if you subtract equation 1 from equation 2, 2 minus 1 will give us what?
X raised to m into x minus.
So if we subtract 2 minus 1, what will we get? So this will cancel everything. This will cancel with this. And we are left with the xm plus 1 minus x power 0. So this is going to give us xs minus s equals xm plus 1 minus x 0 minus x power 0 divided by, no, not divided by, but this is xs minus s. So this means that s equals xm plus 1 minus 1 divided by what? X minus 1. Okay, so this is, again, this is just to remind you how to derive the formula for the geometric series. So this is x m plus 1 minus 1 divided by x minus 1. In fact, we will use it again today. So the geometric series will be used a lot in these recursion tree calculations. So this is just to remind you how to derive it. Okay, so now applying this, what's x here? X is 2, right? So this is 2 times h plus 1 minus 1 divided by 2 minus 1. Okay. Now this is for the binary, complete binary tree. But for any, you can generalize this for a k-ary tree. For any k, for a branching factor of k, not necessarily 2. So you will just substitute k for 2. So here, this becomes k over I. This becomes k power h. This becomes log L power k. And this becomes, we can just rewrite this as sigma I equals 0 to h k times I, which is equal to k h plus 1 minus 1 divided by k minus 1. Okay. Anyway, now that was just a review of the mathematical relations for a complete binary tree. Why did we review them? Because the recursion tree that we will be constructing, it will be a complete, not binary tree, but k-ary tree. So what determines if it's a binary or a trinary tree? What determines this? It's the branching factor. So how many branches? So this is binary because we have 2 branches. Okay. So generally speaking, so now what will be the the first step in solving in trying to calculate the number of operations in a tree like this is calculating the height. So what's the height? Height h in this case equals what?
N minus 1.
So we go from n to 1, so this is log n base 2. Why? Because we are going in a, we are dividing, we are going n over 2, n over 4, and so forth, until we get to 1. So the number of levels, well, in fact, the number of levels excluding the the total number of levels is going to be log n base 2 plus 1, but h is the number of the last level. So this is level 0, level 1, level 2, and this is the level here is going to be level h minus 1, and the base level is level h. So the base level is going to be level h. The levels are going to go from 0 to h minus 1. This is if we go all the way to 1. So this means that total number of levels is h plus 1. The number of internal levels is h, right? And the height is going to be h, which is the number of edges here. Okay, so it's, in this case, it's log n base 2. Then we calculate the number of leaves, L. Now the number of leaves is going to be k power h. So in this case, it's going to be, what is k power h? K is 2 and h is log n. So what's this? So this is n, because we can do this. Remember, we can do this switching. Log n, so we can do, this is equal to n log 2 base 2, which is n power 1 or n. Of course, this is not a surprise for us. We know that for merge sort, the number of leaves of the tree is n. Okay. By the way, recursion tree method, you will need multiple examples. We need multiple examples in order to understand it. So when we go through the second example, things will make more sense. Now it's we're trying to use this systematic mathematical method to analyze an algorithm that we have already analyzed easily. So we have already analyzed merge sort easily. We're applying this systematic method in order to understand it. Then we will apply it to a harder example, and when we apply it to a harder example, it will make more sense. So what we have calculated here is the height, which is log n base 2. The number of leaves is n. When we calculate the number of leaves, we can calculate the cost for the base level in the tree by multiplying this constant by the number of leaves. So the base cost equals L times D, or DL. D times L. And that's going to be D n, which is theta of n. And again, this is not a surprise for us. All what it means is that the cost or the number of operations at the base level in merge sort is theta n. Why? Because there are n leaves in the tree, n base cases or n subarrays of size 1, and the cost for processing each one of them is a constant. So that's all what it means. So this is the base cost. Now what's the internal cost? So the internal cost, we just do the summation at each level. So the cost at this level is Cn. The cost at this level is 2Cn over 2, which is Cn. And the cost at this level is 4Cn over 4, and this is another Cn. Again, what this analysis is telling us is that the cost or the number of operations at each level is the same. So we can simply multiply this by the height. Okay? So we'll do this and multiply it by the height. Then we will do an example in which we cannot just multiply. So this is the base cost. The internal cost or the recursive cost equals Cn times the number of internal levels. The number of internal levels is h because they go from 0 to h minus 1. From 0 to h minus 1, there are h of them. So Cn times h. So this is Cn times, what's h in this case? H is log n base 2, which is theta of n log n. Now the total cost equals the base plus internal, and this is theta of n plus theta of n log n, and this is theta of n log n. So this is just a lengthy way of reaching the answer that we have already reached easily. But I think it's it's a good idea to just apply this recursion tree method to an easy case that we have analyzed before. Okay, so to summarize, we first calculate the height, then we calculate the number of leaves. After we calculate the number of leaves, we calculate the base cost. Then we look at the cost at each level. If it's the same, we just multiply it by the height. If it's not the same, which is, as it will be the case in the next example, we'll have to do a summation, as we will see in the next example. Now, why are we treating the internal cost and the base cost differently? Why are they being treated differently here? Yeah, because each one of them is subject to a different formula. Remember, it's T of n equals D if n equals 1, and it's equal to 2t of n over 2 plus theta of n if n is greater than 1. So, this base case, this base corresponds to one level. So this is treated differently. So we calculate the base cost separately because it's subject to a different formula. And everything else is calculated according to this part of the equation, or the definition of this function. Okay, so let's now another example. Okay, so let's leave this. Okay, so the example is T of n equals 4T of n over 2 plus Cn if n is greater than 1, and it's equal to D if n equals 1. Now, when you see this for the first time, you may think that this doesn't make sense. This is 4 and this is 2. Well, generally speaking, what does this 4 represent? So this is a recurrence that describes a divide and conquer algorithm. Into how many subproblems does it divide the original problem? Into 4. So this is a divide and conquer algorithm that divides the original problem into 4 subproblems, but each problem is half the original size. Okay, so if it divides it into 4 subproblems, the size of each subproblem is not necessarily 4. It's not necessarily 1/4 of the original size. Anything is possible. And in fact, we would like to learn how to solve any recurrence with an arbitrary value for the number of subproblems and an arbitrary value for the division ratio. Okay, so in general, if you have T of n equals AT of n over B plus f of n. So generally speaking, A is going to be number of subproblems. B is going to be the division ratio. And what's f of n? No, f of n is not the base. Yeah, it's the combined time plus the divide time, both of them. When you add the combine and the divide, that's f of n. So f of n is divide time plus combine time. Okay. So just to convince you that these two factors, that A and B are not necessarily the same, I don't have an example for an algorithm like this to give you now, but I have an example of an easy algorithm for which A and B are not equal. This simple algorithm is binary search. So binary search is going to have an array of size n, and it's going to divide it into 2 arrays of size n over 2, right? And you go until you get to size 1, if you get all the way to size 1. Now, what's the recurrence for binary search? T of n equals what? So the time for solving a problem of size n is equal to, how does it relate to the time needed to solve a problem of size n over 2? So do we have 2 of them or 1 of them? One of them, because in binary search we only process 1/2. So in binary search we process a half and we discard a half. So in binary search it's going to be t of n over 2 plus, what's the divide time plus the combine time in binary search? How much time do we spend to divide the array in half? Constant. And how much time do we spend in combining in binary search? There is no such a thing. Yeah, there is no combine in binary search. So the combine is 0 and the divide is 1. So for binary search, the formula is t of n equals t of n over 2 plus constant. This is if n is greater than 1, and if n is less than or equal to 1, we have a constant, d. So this is binary search. So I'm bringing binary search here as an example to show you that this factor here is not necessarily equal to this. So yes, we divided it into 2, but we only processed one of them. So A and B are not necessarily equal all the time. Now, okay. Now let's analyze this. Let's get back to this example. 4t of n over 2. So it's going to look like this. Let's try to draw the recursion tree. So we'll say, okay, we have Cn, and then we have, no, let's do it in steps. So let's, okay, t of n is Cn, and we have 4 t of n over 2, t of n over 2, t of n over 2, t of n over 2. This is one substitution. Then we substitute one more, and we get what? Cn. Then what do we get here? So we get 4 what? What should I write here?
over 4.
Yeah. Why over 4? No, there are 4 of them, but the division ratio is 2, which is the same as merge sort. So remember, the division ratio is the same as merge sort because this is by 2. We're not dividing by 4. So the ratio is the same as merge sort. So this is simply Cn over 2, Cn over 2, Cn over 2, Cn over 2. And then at the next level, we will have Cn over 4. And each one of them will have Cn over 4, Cn over 4, Cn over 4, and the same for each one of them. So at the end, we'll have the base, and we will have these in the base. Now the number of leaves here, do you think the number of leaves will be the same as merge sort, or larger or smaller?
Larger.
Why will it be larger?
4.
Yeah, because we are branching by 4. We are branching by 4, which means that we should get a lot more leaves at the base. Okay? So we analyze this. First step is calculating the height. Height h. Now the question is, will the height of the tree here be the same as merge sort or different? No, the height is going to be the same because this factor is the same. Because we are dividing by 2. So we will keep dividing until we get to size 1, right? So this division ratio is what determines the height. But this branching factor determines the number of leaves, right? So if we divide by 2, the number of levels that will be taken until we get to size 1 is going to be the same as merge sort. We just divide by 2. So same number of levels as merge sort, but we are branching faster. Here we're branching by a factor of 4. So by the time we get to the base, we'll have a lot more leaves here. Okay, so the height In fact, we can generalize this. The height is always log n base b, where b is the division ratio. Okay, so log n base b, and this is log n base 2.
Right.
Now, number of leaves, L, is going to be equal to, so the number of leaves is going to be the branching factor times the height. So it's going to be A times H. The branching factor, which is the, the degree of the tree. So this is A. The branching factor is, what is the branching factor here? 4. So it's going to be 4 power H. So it's going to be 4 power H, 4 power log n base 2. And this is what this is. We can do this swapping. So this is n log 4 base 2, which is n squared, which makes sense. So we have n squared leaves now because we are branching faster. So this n squared compared to n in merge sorts, this n squared should not surprise us. It's expected. We expect to get a lot more leaves. Now, given the number of leaves, we can go ahead and calculate the base cost. So the base cost equals L or dl, and this is d times n squared, and this is theta of n squared. So now we have theta of n squared at the base. Okay? Now we need to calculate the internal cost. The key step in calculating the internal cost is finding the cost at each level and finding a formula between the level that relates the level number to the number of operations at that level. Level number with the number of operations at that level. I think I should erase this now to have more space. Okay. So now this is level 0. At level 0, I have Cn operations. Now at level 1, how many operations do I have? 4 Cn over 2, which is 2 Cn. So now it's different. So I won't be able to multiply now. I will have to do a summation. At level 1, at level 2, I have, how many of these will I have?
16 Cn.
I will have 16 of them. These are 4, and I have 4, 4, 4. So there will be 16 of them. 16 Cn by 4, which is 4 Cn. Usually, level 0, 1, and 2 will be enough to deduce the formula between the number of operations and the level number. So, number of operations at level I equals what? What's the mathematical relation between number of operations at level I and the level number? Yeah, so it's 2 power I Cn. 2 power I Cn. This is usually the key step in solving this. Figuring the relation between the number of operations at a given level and the level number. This is the key step. Now, once we write this formula, it will be a matter of doing the summation. So now the internal cost is equal to sigma I equals sigma of 2i Cn. I goes from 0 to, no, this is h minus 1, and this is level h. So the last internal level is level h minus 1. So this is going to be h minus 1. And this is equal to Cn sigma I equals 0 to log n base 2 minus 1 of 2 power I. And what kind of series is this? So this is a geometric series. And what's the value of x? What's the value of x? What's the base? 2. Yeah. So this is Cn 2 power, this is m. So this is m. So m plus 1 is going to be log n base 2. 2 log n base 2 minus 1 divided by 2 minus 1. And this is Cn, this is n log 2 base 2 minus 1 divided by 1. So this is Cn squared minus Cn. So this is the internal cost, this is the base cost, which means that the total cost equals dn squared plus Cn squared plus minus Cn. So this is theta of n squared. So what this analysis showed us is that the number of operations here, the number of operations at the base is quadratic, and the number of operations internally is quadratic. So asymptotically, the number of operations that are performed at the base level is asymptotically the same as all the operations that are performed internally. And why is that? Because of the fast branching. So we have so many leaves at the base level. Okay?
How did we come in?
So this is n power 1, right? Okay, so let me summarize again. So let me summarize this. So we are given this recurrence equation. So we construct the recursion tree by, in fact, now we can skip these steps and we can go immediately to this, because we just go to this function f of n. We look at this. So this is f of n. Then how many branches? We just look at this number. This is 4. So we make 4 branches because this is 4. So we have 4 branches. What's the size of each? What's the number of operations for each one? It's this divided by this b, the ratio. So this is b, this is a. So this is Cn over 2 because this is b here equals 2. Cn over 2, Cn over 2. And we just branch another 4, and this is Cn over 4, and so forth. Now, in order to calculate the total number of operations, first we calculate the height. The height is going to be log n base b. If the recurrence is of this form, for any recurrence of this form, the height is going to always be log n base b. And b in this case happened to be 2. So it's log n base 2. Then we calculate the number of leaves. Number of leaves is going to be the branching factor or the number of subproblems, which is A. In this example, it's 4. So it's 4 power h, the height. 4 power the height. So it's 4 power h. Then we calculate the number of leaves. The number of leaves will tell us the base cost, will tell us how many operations we are doing at the base level. So we calculate the base cost. Then we calculate the internal cost, or the recursive cost, the number of operations internally. And the key step is to find the mathematical relation between the number of operations at each level and the level number. So the number of operations here is Cn, number of operations is 2Cn, this is 4Cn. So we deduce the relation between the number of operations at level I and I itself, and this is 2 power I Cn. Then once we get this figured, we do the summation from 0 to h minus 1, level 0, 1, 2, level h minus 1. Level h is the base level. Okay, level h is the base level, and we calculate the summation. Okay, any questions on this?
In this 2 raised to I, can you give us in terms of A and B?
In terms of well, so this 2 here is what? It's A divided by B. So this 2 is A divided by B here. But generally speaking, you will have to calculate the number of operations at each level, and then figure out the formula. Okay, any questions? No questions on this? Okay, so let's do a quick example. So we have like 8 minutes. So these 8 minutes are enough for doing a quick example like binary search. Okay, so for binary search, A equals 2, A equals 1, and B equals 2. So T of n equals T of n over 2 plus constant. Now, how do we draw the tree for this? Well, the tree is going to be C. At level 0, we have C. Now, at the next level, how many branches do we have? No, 1. It's A. So the number of branches is A. So we only have 1 branch. And this is going to be C, but it's not a function of the size. So it's not, C is just a constant. So the combine time or the divide time, well, in binary search it's the divide time. The divide time is not a function of the array size, right? To divide an array in half, the divide time is just a constant. It doesn't depend on the size of the array. So it's just a constant. So it's going to be a constant at all levels. And then finally, when we get to the final level, we'll have a D, because this is n greater than 1, n less than or equal to 1. We have a D. And you know, remember that we can always ignore constants. So this is level 0, level 1, level 2, and this is going to be level h minus 1, and this is level h. So if we apply the procedure, h here equals log n base b, and what's b in this case? B is 2. B is this thing, right? So here, this is b, and this is a. Log n base b, log n base 2. Now, what's the number of leaves? Of course, it's obvious, you know, what the number of leaves is. The number of leaves is 1. So, but if we apply the formula, so it's going to be 1 power h, or 1 log n base 2, which is 1. So we have 1 leaf. So the base cost equals d, and the internal cost. Now, is the cost the same at all levels?
Yes.
It's the same at all levels. So we just multiply it by h. So it's going to be c h, or c log n base 2, and total cost equals d plus c log n base 2, and that's theta of log n, which is what we already know about binary search. So this is an easy example. Why? Because the branching factor is 1, so it's going to be just one line. And because the cost at each level is the same, so we didn't have to do a summation. So it's always easier when the cost is the same at all levels. So we don't have to do a summation. We just multiply by the number of levels. Okay, so it looks like we will not get to cover the master theorem today, but I will talk about it briefly. In fact, the master theorem is a theorem that will just tell you what the running time is, but it's based on the recursion tree method. So it's based on solving the recursion tree method in general. So people solved it in general and gave you the result, and you can just apply it. It tells you what the running time is by looking at A and B for a recurrence of this form. But we will discuss the master theorem next time.